As a reminder, when we did, here we're converting degrees, minutes, seconds, and radians. We're going back and forth between the two. And we wanted to convert this degrees, minutes, seconds into radian measures. Main reason I'm doing this is extra practice, because we're going to go back and to convert this to radians, we're first going to have to convert that to decimals. 36 degrees, 25 minutes, and 10 seconds. We first convert to degrees, and let's pull up our calculator. We can do this entirely on our calculator. So here you go. Here's your reminder of how to type this in. This is 36 whole degrees plus 25 minutes. That's 25/60ths of another degree. It's not an entire degree. It's that fractional part of another degree. And then 10 seconds, that's a very little part of another degree. That would be 10/3600ths of a degree. So we have 36.419. And I'm going to leave that on my calculator just to, so I'll end up with an exact answer. So it's 36.419 degrees. And again, to change that to radian measures, we're going to multiply by pi radians over 180 degrees, because again, what we're really multiplying by there is 1. My degrees will cancel and leave me with just radian measures. So to do this, I'm going to multiply by pi and divide by 180. So just bring back your calculator. Do times pi, and again, I left the exact answer here. So times pi, oops, let's try that again. Times pi, or the answer times pi. And then divide that by 180. And you get about 0.6356. About 0.6356 radians. Reminder, 3.14159, pi radians, that's 180 degrees. Half a pi, that's 90 degrees, that's about 1.57. Would be half a 180, that's 90 degrees. So the relationship here, you take 1.57 and take about a third of it, because 36 degrees would be about a third of that 90. So it should be actually a little bit more than a third, and you do see that, that's fairly accurate. Now let's go the other direction. Let's go from 5.1285 radians to DMS. That's degrees, minutes, seconds. We don't want it as a decimal. We want to take your decimal, change it to degrees, minutes, seconds. So we got this many radians. In order to change that to degrees, I'm going to multiply by pi radians on bottom. So my radians will cancel, and 180 degrees on top. Multiplying by 1 there. Radians do cancel. So in my calculator, I'm going to type that 5.1285 times the 180, and I'm going to divide by pi. And use my pi button so it's exact. So 5.1285 times 180. Enter. I'm going to divide that by pi. Enter. I get about 293.84 degrees. What was that again? 293.84. But don't clear your calculator, because that 293.84 is not exact. That's an approximate. I'm just putting that there for a placeholder. Because now to convert that to degrees, minutes, seconds. Okay, this remnant, this leftover, this 0.84 whatever, is a partial another degree. And to find out how many minutes that is, it's not a full degree, it's 0.84 of a degree. So therefore it's 0.84 of a full degree, which is 60 minutes. So in order to find out how many minutes that actually is, you're just going to multiply the two. So let's bring my calculator back up. I'm going to take off the 293, so I'm just left with the fractional part. So let me go ahead and put the 293. You got 293 degrees. Okay, now I took that off. I'm going to multiply my remnant times 60. You're left with 50.484. And again, that 50 degrees is how many full minutes you have. So I have 293 degrees. I have 50 full minutes. But then again, like I said, you've got that extra remnant there. So let's take off the 50. So let's do minus 50 and take that off. And I'm left with 0.484, 313, 9, so on and so forth. That's a remnant of a minute. So multiply, a remnant of a minute is called a second. So multiply by 60 again, and you're going to find out how many seconds you have. That'd be 29.05 seconds. So 29 seconds. And like I said, you could go on further than that. Make sure that, let me make sure that wasn't supposed to round. Yeah, that's right. So 293 degrees, 50 minutes, and 29 seconds is what 5.1285 radians would be. Okay, next up, arc lengths and central angles. And what an arc length is, this is a little bit different. You've probably done this in the past. I think there's actually a chapter in geometry that concerns this exact same thing. Arc lengths and central angles. Going back and just a real quick review from the geometry. What a central angle is, a central angle has its center at the center of your circle. Alpha here is a central angle. An arc length. Okay, when we're talking about arc lengths, we're not talking about the distance all the way around a circle. That's called circumference. Circumference. That's the distance all the way around a circle. We're talking about a portion of that. And let's go back to geometry and show you how hard this was back in geometry to do. Let's say that alpha was a 60-degree angle, and you had a radius of 6. I want to find out what arc length do I have right here. What's the distance from here to here, which, by the way, arc length, don't ask, is abbreviated with S. S is the abbreviation for arc length. I don't know. And here's how we work this in geometry. We would say, okay, the distance all the way around the circle, that's the circumference. So let's first find the circumference, and the way you found that was either pi times diameter or 2 times pi times the radius. That was your formula. And you would do, okay, 2 times pi times radius. The radius is 6 over here, so that'd be 12 pi. That's the distance all the way around the circle. But we don't want the distance all the way around the circle. We just want this 60-degree arc right here. And then you would say, okay, 60 degrees. Well, there's 360 degrees all the way around a circle. So the portion that we want is 60 degrees out of those 360, or 1/6. We don't want the entire circumference. We only want 1/6 of it. And that's probably the way you've always worked this. Well, if the whole distance around it was 12 pi, and we only want this 1/6, and can you see that if you actually took and split this? Does it make sense that it would be about a 1/6? Y'all see that? It splits into 6 equal pieces, so therefore we're looking for a 1/6 of the entire circumference. So you take your 12 pi over here, and you divide it by 6, you take a 1/6 of it, so the length of this arc would be 2 pi. 6.28. There's an easier way now. Okay? And that's odd that you're in pre-calculus. Now we're going to teach you the easy way in pre-calc. Okay? You have this formula. And look down here. We know that circumference is 2 times pi times the radius. Again, notice from your formula here, circumference is 2 times pi times radius. Doesn't that 2 pi look familiar? 2 pi, I believe, would be the distance, the angle formed by the entire circle. And this circumference formula, when you're finding circumference, that is the distance all the way around a circle. But what if we want a partial distance? Then should we not be able to take out that 2 pi and replace it with the partial distance angle that we want? Now here's the important thing to remember. Circumference 2 pi r. 2 pi is a measurement of radians. That is a radian angle measure. So what we can do is we now have this formula. What if we want to find a partial circumference? Right here it is. Arc length is equal to simply the angle times the radius, which comes from this. Arc length, which if you're looking for the entire arc length, the entire circumference, yeah, it's C. But arc length is equal to the angle of the rotation that you're looking for times the radius. That's it. And you see down here I've got 2 pi is the same thing as 360. That's the entire rotation. So let's try one of these. And let's do it the easy way. The wagon wheel shown below has a diameter of 28 inches. Diameter of 28, so that means the radius is 14. And an angle of 30 degrees between the spokes, what is the arc length formed by each spoke? What's the distance from here to here? And you no longer have to do that 30 degrees over 360. That's a 12th of the whole circle. Find the entire circumference, multiply it by 12. Now you don't have to do that anymore. Arc length is equal to the angle. Now you got to be careful. You can't plug in 30 degrees. And you'll find out, not only in this class, but in physics as well, anytime you're trying to plug an angle into a formula, you're not going to plug in 30 degrees. You're going to change it into radian form, and you're going to plug that in. So 30 degrees is a radian. Let's think about that, guys. Pi is 180. What can you divide 180 by to give you 30? So is that not pi divided by 6? Pi over 6. 30 degrees, pi over 6. The angle is equal to, or the arc length is equal to the angle times the radius, which in this case was 14. So the exact answer, you can do 14 pi over 6, which reduces to 7 pi over 3. That's the exact answer. Now be careful. This is not an angle. It looks like an angle. That looks like, oh, that's 210 degrees. No, that's not what that is. That's a decimal. That's an arc length. That's the distance from here to here. And you can estimate it. The distance from here to here is 14. That looks like it's going to be somewhere around maybe 5 or 6 to me. So we're going to do 7 times 3.14159. 7 times your pi button divided by 3. Has anybody got that typed in? 7 times pi divided by 3. 7.33. So the distance from here to here is about 7.33. And again, you can see in relation to the 14, that looks pretty accurate. Okay. Arc length, and if you haven't already written it down, arc length is equal to the angle times the radius. Simple formula. Arc length equals angle times the radius. The angle must be in radian form. Another one, find the length of the arc intercepted by a 45-degree angle on a circle that has a radius of 8 inches. Arc length is equal to the angle times the radius. 45 degrees. Somebody tell me, what is that angle? Pi over 2 is 90. There you go. Pi over 2 is 90. So take 90 and divide it by 2 again, and then it gives you 45. So it's 180 divided by 2 divided by 2, which is 180 divided by 4, times the radius, which is 8. Two and 1 gives me, whoa, let's undo that. I have no idea what happened. 2 pi, or about 6.28. So you have a 45-degree angle, a radius of 8 inches, and you want to know what's that arc length that's cut off. It's about 6.28 inches. This reminds me of an ACT type problem because it's got all this wording, and there's like 10,000 numbers in this problem, and you only use 2 of them. There's lots of extra information here. For 4 years, U-2 spy planes flew Renaissance over the Soviet Union, collecting information for the United States. U-2, designed to fly at 70,000 feet, well out of range of Soviet guns, carried 12,000 feet of film, wow, and a camera that could photograph a path 2,000 miles long and about 600 miles wide. That's huge. Find the central angle to the nearest degree that intercepts an arc of 600 miles on the surface of the Earth that has a radius of 3,150. So, you know what? Those first 2 or 3 sentences, completely worthless information. They was just trying to amaze you with their knowledge of numbers here. Here's all we're looking for. Find the central angle to the nearest tenth of a degree that intercepts an arc of 600 degrees. So we got a 600-degree arc, and we have a radius of 3,950 miles. S. Arc length is equal to the angle times the radius. All we're doing on this one, we're looking for the angle instead of the arc length. They give you an arc length of about 600 miles here. and they give you a radius of 3,950 miles. So to find the angle, you divide. One step, divide here, 600 divided by 3,950. Let me caution you on something though, because when you divide that, I'll do it right here. 600 divided by 3,950. You get 0.1518. Go back to your problem. Find the central angle to the nearest tenth of a degree. When you use this formula, alpha is always in radians, not degrees. So even when you work it backward, it's going to give you an answer in radians, not degrees. So we're going to take our radian measure, which again is about 0.1519, about 0.1519 radians, and we want that in degrees. So we multiply by what over what? Good. 180 over pi. So that my radians will cancel. So pretty much take your calculator, multiply your answer times 180, enter, divide that by pi, enter, and you get about 8.7 degrees. Very small angle. Find the central angle, just like the last one. Find the central angle in degrees that intercepts an arc of 3 centimeters. So you got the circle. You have an arc of 3 centimeters, and you have a radius of 50 centimeters. We want to know what that degree, what that measure is. Arc length equals angle times radius. The arc length is 3. We're looking for the angle. The radius is 50. 3 divided by 50, I believe that would be 0.06. Alpha is 0.06. But again, that's 0.06 is in radians. So you take your 0.06 on your calculator. Very easy. 0.06. You'd multiply times what? Good. And divide by. And divide by pi. Let's try that again. Divided by pi. So about 3.4 degrees. Very small angle. That was 0.06, which makes sense. 0.06 radians. You have such a small arc length. This long radius of 50 degrees, but such a small arc length in comparison to it. Yeah, that is going to be a small angle. Linear and angular velocity. Probably be the last thing we have time for today. Linear and angular velocity. And we're going to watch a video here in a second on this. But let me try to explain it before we do. Velocity, guys, when we're talking about velocity, we're talking about a speed. How fast are you traveling? Linear velocity is, okay, we start at point A, traveling to point B. How quickly can we get there? Okay. Now, what if you're traveling on a circle? We still, well, think about track, right? Let's say that you had a perfectly circular track and you're running around this track. You have a linear velocity. That's how much, let's say the track is a mile long. And it takes you an hour to travel that. That'd be a slow rate. But let's say it took you an hour to run around that track. You're traveling at 1 mile per hour. Okay? That's a linear velocity. Now, there's another type of velocity called an angular velocity. And what an angular velocity is, it's not how much distance that you're displacing over a certain amount of time, but it's what angle are you displacing. You're spinning in the circle, and let's say that it takes 1 second, I guess you could say, 1 second to travel 30 degrees. The same way that you have 30 miles per hour, 20 feet per second, you also have, in that case, would be 30, you could say 30 degrees per second. That's an angular velocity. How quickly are you spinning? Okay. And you got to be careful about this, because what if you had 2 different size circles? Okay. Now let's relate angular velocity to linear velocity. Let's say that it takes you 1 second, or let's go 1 second to travel all the way around this circle. So you're traveling 360 degrees per second. Now let's go over here. And let's say that it takes you 1 second to travel all the way around the circle. You're traveling at 360 degrees per second. That's angular velocity. Compare that to linear velocity. Okay, it took you 1 second to go around this circle. How far did you travel? Well, whatever the circumference is. That makes sense. It took you also 1 second to travel around this circle. Which one was going faster? Now, when I say faster, they were going the same speed as far as angular velocity. But circle A or circle B, which one was traveling faster? Was it? Which one displaced more distance? Which one traveled? Because they traveled, it took them both 1 second to go all the way around it, but which one went the greatest distance in 1 second? B. They traveled a whole lot farther in 1 second. So here's you a good way to relate this. You've got a CD. Well, let's let this be your CD over here. And you've got 2 bugs that's sitting on your CD. You got bug 1 and you got bug 2. See where I'm going with that? If they're not setting the same distance from the center of the circle or the center of the CD, one of them's traveling faster. Think of it like this. You're on a merry-go-round. Are you traveling faster? I bet you never thought about this. Are you traveling faster if you set in the center of the merry-go-round? Or are you traveling faster if you're setting on the outside of the merry-go-round? A whole lot faster. Now, if you're setting in the center, think about it. If you're setting dead center of that merry-go-round, how fast are you going? You're not. You're not moving. Right? You're just spinning. You have an angular velocity, but if you're setting in the dead center, how much distance are you displacing there? None. You're staying still. You're just spinning. Now, if you're on the outside of the merry-go-round, are you actually displacing distance? Yes. Yes. Now, which one would you probably get drunker at? Probably the middle. Then I don't know. That'd be a good. That's y'all's homework for tonight. Go find your merry-go-round and see, do you get sicker if you sit on the inside or on the outside of the merry-go-round? But that's the difference between linear and angular velocity. So if you haven't already, copy these down. Linear velocity is how far you travel divided by how long it takes you to get there. Miles per hour, feet per second, like she said in the video. How far you're traveling, which we're traveling around circles here, right? So the distance you travel, is that not your arc length? And we remember arc length from our previous formula, divided by the time that it takes you to get there. So velocity, linear velocity is arc length divided by time. Angular velocity is the amount of angle you displace in a certain amount of time. So your angular velocity would be angle divided by time. So let's work a couple of problems, then we'll stop for the day. What are the angular velocity in radians per second and the linear velocity in miles per hour of the tip of a 22-inch lawnmower blade? There's your blade. It's 22 inches. Rotating at 2,500 RPMs. Now let's explain what RPMs are. An RPM, okay, the R in RPM stands for revolutions. So a revolution is one complete cycle. Okay, that's going around one whole time. So this lawnmower blade spins around 2,500 times in 1 minute. So therefore, we want to know, okay, let's start with angular velocity. We might not even need our formula on these. Angular velocity. How much is your angles changing in that? Let's say we want it in angular velocity radians per minute. So we want to know how many times is our angle changing, or how is our angle changing per time? Angle over time. Well, what is our angle displacement here? If it's traveling 2,500 RPMs, what is a revolution? It's 360 degrees, right? One revolution is 360 degrees, or since they want it in radians, instead of 360, we're going to go 2 pi. So it goes 2 pi 2,500 times. So to find out how many times, or find out what that angle is, we're going to take that 2,500, multiply it by the 2 pi, and I believe that would be 5,000 pi. And that's my angle displacement. And if you want to change that to actual degrees, that'd be 5,000 times 180 degrees. That's a lot. Okay, that's a huge number. And what's our time there? It's this much angle in 1 minute. That's your angular velocity. And that's in radians per minute. Let's look at it just out of curiosity. Let's look at that as degrees. Somebody's got a calculator. Do that 5,000 times 180. Got 9 with how many zeros? 5 zeros. If you did it in degrees per minute, 90,000 degrees per minute. 360 is 1 revolution. So in 1 minute, your blade is traveling 90,000 degrees. That's your angular velocity. Now let's look at linear velocity. Linear velocity V. Linear velocity. Velocity is equal to displacement or arc length divided by time. So we've got to find out in that 1 minute our arc length. It's traveling 2,500 revolutions, but what is a revolution? A revolution is the distance from here all the way back around to here. So how do we do that? We can use that pi d coming up. Pi times diameter or 2 pi r. The radius is 22 inches. We plug that in here. That's 44 pi inches. That's 1 revolution. When it goes around 1 time, it travels 44 pi inches. But it's not going around 1 time. In that 1 minute, it's spinning 2,500 of these. Spinning around, traveling that distance 2,500 times. So what we're going to do is we're going to take our 44 pi. We're going to multiply by the 2,500 times that it does that. And it does that in 1 minute. And that's in inches there. So 44 pi. I've got you right here. You can leave it exact. I want to do it as a decimal just to make it more real to you. 44 times pi times 2,500. That'd be 345.575 inches per minute. So in 1 minute, if there's a bug on the tip of that lawnmower blade, in that 1 minute, that bug traveled 345,575 inches. Let's make it more real. How many feet's that? Divide by, good, 28,797 feet. We want to know miles. 5,280. 5,280 feet in 1 mile. It traveled in 1 minute. If there is a bug on the tip of that lawnmower blade, it traveled 5.45 miles in 1 minute. Okay, so why should you not put your hand under a lawnmower when the blade is moving? Because it's moving very fast. Okay, and that's probably pretty accurate. 25 RPMs or 2,500 RPMs. Anything that's traveling that fast, if it had even that's nearly a 2-foot blade. A 2-foot blade, the tip of that thing is traveling over 5 miles in a single minute. We want to take that answer though, and we want it in miles per hour. So how do we get inches into miles, and how do we get minutes into hours? We use those conversion factors like I was talking about a while ago. I know that, well, let's change minutes first into hours. How many minutes is in an hour? 60. And here's what you do. Minutes is on bottom here. We want it on top here. 60 minutes, 1 hour, same thing. So really I'm multiplying by 1 there. Minutes cancels with minutes. Now I'm in hours. 345,000. Let me give me a little bit of room here. 345,575 inches. I know that there are 12 inches and a foot. Notice where I put inches on the bottom, so to cancel with the top. Now I'm in, look, now I've got feet and hours. Now I'm in feet per hours. I want miles per hours. So I got feet on top. Let's say 5,280 feet is 1 mile. Feet cancel. You see now I'm in miles per hour. That's conversion factors. You do a lot of that in chemistry. So on top, here's how I'm going to type this thing in. I've got 345,575, and I've got to multiply it by 60. On bottom, I've got 12. I've got to multiply it by 5,280, and then I'm going to divide it. So, it's still in my calculator up there. 44, let me type it in again so I'm exact. 44 pi times 2,500. I've got to take that number and we're going to multiply it by 60. That's the top of your fraction. The bottom of your fraction is, let's go ahead and do this, divided by 12 times 5,280. And you get 327.25. So let's just call it 327. So that's 327 miles per hour. So that's how fast you're traveling. Again, if a bug is on the tip of that lawnmower blade, and it's on the tip because it's all the way out, if a bug's on the tip of that lawnmower blade, it's traveling at 327 miles per hour.